Do you remember that star system that was making headlines a while ago? The star is called TRAPPIST-1. It's a small M-class red dwarf star, 39 light-years away from Earth, with a collection of Earth-sized planets orbiting in close proximity. I've made a few news segments about it. I think one of my first news segments ever was about this star system. It's a really interesting place, because even though the star is small, dim, and cool, it has 7 Earth-sized planets in a very close orbit, with more than one of them orbiting in the star's tiny little habitable zone. In the most recent month, a study was published in the Astrophysical Journal that experimented with radiation and chemistry models for all of the planet's atmospheres. In their abstract, the authors say, quote, "The TRAPPIST-1 planetary system provides an unprecedented opportunity to study terrestrial exoplanet evolution," unquote. This is because a star system that has 7 very similar planets, 7 Earth-like planets, is like having 7 concurrent experiments, or 7 petri dishes, that each have their own variables, like their atmosphere and surface geology, but are all exposed to the same light source, the same dim dwarf star. It's like a giant scientific experiment that's already been set up and put in motion 8 to 10 billion years ago. The authors explain that an M-type dwarf star has several properties, like variability, CME activity, and radioactive emissions, that would work to decompose volatile compounds on the surface of its planets. Additionally, in such a cozy star system, planetary impacts could be more frequent. These incredible events can pulverize the crust and turn millions of square miles of rock into magma. The heat and pressure would boil away volatile compounds. These volatiles include ammonia, methane, nitrogen, and water, among many others. Basically, volatiles are building blocks for larger organic molecules, so if a planetary environment boils away all of its volatiles, there isn't really a way for carbon-based life to form. There isn't any chemical infrastructure. And without an ecological biochemistry to help regulate the planet's climate, the climate is likely to just go on a runaway evolution of its own until it's totally uninhabitable. And unfortunately, that appears to be the case for most of the planets of the TRAPPIST-1 system. The researchers created a variety of models for each planet based on its known characteristics, and established, quote, "equilibrium climates with self-consistent atmospheric compositions," unquote. These equilibrium states are the final, stable product of a runaway greenhouse effect, which would fill the atmosphere with carbon dioxide and boil away its water. The atmospheric pressure increases because of geological outgassing and the volatiles on the surface being boiled away. Every single one of the 7 planets, under most of the climate models, ends up in some kind of post-runaway equilibrium state, where the temperature is simply too hot to be habitable. But there was a few models for 2 of the TRAPPIST-1 planets that would produce a habitable climate, with habitable temperatures, and a presumably habitable surface. The authors say, quote, "Our simulations show a range of surface temperatures, most of which are not habitable, although an aquaplanet TRAPPIST-1e could maintain a temperate surface given Earth-like geological outgassing and CO2. We find that a desiccated TRAPPIST-1h may produce habitable surface temperatures beyond the maximum greenhouse distance," unquote. So Planet E in the TRAPPIST-1 star system could potentially be a water world. And if it is an ocean planet, there's a strong chance that it could host carbon-based life. Although water worlds have their own complications, which I talked about in detail in a recent news segment about a study that estimated that 35% of the known exoplanets are possibly water worlds. As for Planet H, it's the smallest planet in the system, between the mass of Earth and Mars, and it orbits the farthest out, so an initial estimate would suggest that it might be cold and frozen. But Planet H is on the snow line, which means that it's right at the edge of the habitable zone, where water is mostly frozen, but there's still the potential for liquid water. What the researchers found with their models was that this planet could potentially have a habitable climate if the atmospheric greenhouse effects trapped enough heat to counterbalance the relatively low incoming thermal energy from the star. This is all really interesting stuff, but it's important to clarify that these are just models based on our current data. They're not hard observations from out in the field. To get those, we'd need to send a spaceship with scientists and drones 39 light-years out into space. Or we would need a really powerful telescope. It just so happens that in the near future, we're going to be launching the James Webb Space Telescope, and it'll be powerful enough to measure the atmospheric composition of distant exoplanets, including those in the TRAPPIST-1 star system. When the James Webb Space Telescope goes online, we'll be able to get way more information on these exoplanets than we have now, and we'll be able to learn so much more about them. We'll be able to tell for sure if TRAPPIST-1e is a water world. We'll be able to see if TRAPPIST-1h is covered in a dry Serengeti, or if it's covered in glaciers and ice sheets. In general, we'll be able to examine more exoplanets in much greater detail, and identify those with atmospheres that are suggestive of life. It'll be the beginning of a whole new era in astronomy and astrobiology, and I am really excited about it. I can't wait.